All right, hello. I think we're about ready to get started. Welcome to the August 2nd Saturday Stars at the McCarthy Observatory. If this is your first time here, welcome. We host these star parties on the second Saturday of the month, rain or starshine, with what's usually a fairly short talk of around 20 to 30 minutes, followed by observing through a number of telescopes if the sky and weather decide to cooperate. Tonight looks like a pretty good night. So I'll try to keep this quick so you can have more time with the telescopes, although it won't really be dark enough to see much for a while. My name is Mark Polanski. I'm a volunteer here at the McCarthy Observatory, specializing in imaging and asteroid observations for somewhere around 13 years. I'm also a co-founder of the Retro Tech Foundation, an organization created to help reduce e-waste by restoring and finding new life for otherwise obsolete or broken computer hardware. We're working towards opening a museum with fully interactive exhibits in Watertown, Connecticut in the next month or two. In that vein, I thought I'd share some of the influence computers have had in the field of astronomy and how they fundamentally changed how we see the universe. This will be something of a timeline, stepping through the progress of computers and how astronomy changed along the way. We'll start, logically, at the beginning. What did it look like to be an astronomer before computers? What tools were used? How was data recorded or published? How did big numbers and complex calculations get done? This led to the original computers, which may not be quite what you think. Things really started changing once electrons got involved. And each advance in computing led to even more advances as things got smaller, faster, cheaper, and ultimately connected. In the beginning, there was the sky and our eyes, and that was good enough. This isn't meant to be a comprehensive history of astronomy itself. Sufficient to say there were plenty of good reasons to keep track of the sky, from knowing when to plant or harvest crops, to moving over land and sea long before GPS was a thing, to religious significance in almost every culture all around the world. So what did the early astronomers have to work with? The telescope wasn't invented until 1608. For the most part, they had their eyeballs and incredible senses of reasoning and logic. The dioptra was the main tool from around the 3rd century BC onward. A dioptra is basically a sight or a tube without any lenses in it. It's used to single out one or a small group of stars. The dioptra was attached to a base with 2 protractors, one to measure the elevation, or the up and down angle, and one to measure the azimuth, or the side-to-side angle. These were used to precisely measure star positions in the sky over time, enabling Hipparchus to produce the first known star catalog. Using angles to measure things? That sounds suspiciously like trigonometry. Hipparchus is also reasonably well known for being the father of trigonometry, and he put it to good use, cataloging all these stars. How were observations recorded or published? Generally, observations and notes were taken on anything that could be written on or carved into. Wax tablets were a popular medium. They were easy to etch. They could be erased simply by melting the wax. When complete, the wax could be transcribed into a scroll or carved into wood or stone or other more permanent medium. The scrolls could be collected and assembled into books. Prior to the printing press, the only way to distribute books were to handwrite each page out. So books were not exactly produced by the thousands back then. It's sometimes difficult to describe the motions of things in the sky, so some clever humans came up with a 3D model called an armillary sphere, with the Earth in the center and several bands wrapping around representing the sun, the moon, and in some cases planets as they move about the sky. More advanced spheres were mechanized to show the motion of things across the sky. The astrolabe was developed as a simpler two-dimensional version of the sphere and could be used as a star chart or a planisphere, which is something that we still use today as quick reference to find things in the sky for a given time of year. The Antikythera mechanism is probably the most fascinating thing from this time period, created sometime around 150 BC. It's a fantastically complex and precise analog computer. It's effectively an orrery, demonstrating the relative motions of the moon around the Earth and the Earth-Moon system around the sun, using combinations of gears to calculate the relative motions of each object in real time. This was 1,500 years before Copernicus and the acceptance of heliocentrism, the idea that the Earth is not the center of the universe and does, in fact, revolve around the sun. This thing was way ahead of its time. It could accurately predict the moon phases and eclipses, both solar and lunar, even accounting for the moon's elliptical orbit. There's evidence it could even show the positions of the 5 naked-eye visible planets. It's pretty good for the 2nd century BC. It was discovered in a shipwreck off the coast of the Greek island Antikythera in 1901. But it wasn't until about 2005 that the actual functions were revealed via X-ray tomography. The X-rays helped us look inside of it to see the actual intricate gearing mechanisms to understand how it actually worked. And there's far more to it. So I'd encourage you to search YouTube for Antikythera mechanism V2 to find an excellent video of the design and construction of a modern recreation based on those X-ray scans. This was basically peak computing for almost 2 millennia. For most of humanity's existence so far, astronomy was limited to what could be seen by eye and calculated on the equivalent of paper by hand. The introduction of the telescope in the 1600s gave us a better understanding of the moon, the planets, and the stars. As telescopes got bigger and better, more was discovered: galaxies, nebula, comets, and so on. However, any data from these objects were still collected by hand, via notes and drawings from what you could see by eye. In the 19th century, spectroscopy and photography came about in astronomy. Spectroscopy came from the revelation that light contains hidden information. Basically, a beam of light can be broken up into the individual colors or frequencies that make up the beam. Within the dispersed light are brighter emission lines or darker absorption lines. These combinations of lines are unique to each element on the periodic table. This means with spectroscopy, we can tell what something is made of by looking at the light it emits or absorbs. As a side note, when you hear astronomers talking about redshift or blue shift of objects, they're talking about the spectral lines of known elements appearing to move or shift closer to the red or blue end of the spectrum. If the line pattern is shifted towards the red end, it means the object is moving away from us. Shifted towards the blue means coming towards us. Photography enabled humans to observe beyond what their eyes alone could see. The ability to collect light for a longer period of time allowed us to see hidden features in galaxies and nebula, and many, many more stars. In the late 1800s, photographic plates were used to capture spectra from many of the brightest stars in an effort to sort and catalog them. Being able to record the data via the photographic plates meant much more analysis could be done by more people. The amount of data generated started to grow, faster than astronomers could keep up with, so they needed help. And so the first computers came about in 1877, not in the modern electronic sense of the term. At the time, computer was a term given to one who performs computations or mathematical operations. The first computers were people, primarily women, who were exceptionally skilled at performing complex mathematical calculations quickly and accurately. They were tasked with combing through hundreds of photographic plates of stellar spectra, looking for patterns and a means to sort and classify the stars. And they succeeded. They ended up producing a star catalog classification system that we still use today. Many of these women did not get the recognition they deserve at the time, despite immense contributions to our understanding of stars and the nature of the universe. Mary Draper, the wife of Henry Draper, completed Henry's work on stellar classifications after his passing, producing the Henry Draper catalog. Williamina Fleming helped develop the framework of classifying stars based on hydrogen content. Antonia Mora discovered that the star Mizar was actually a binary system of 2 stars, leading to a redesigned star catalog that was adopted by the International Astronomical Union. Anna Winlock rescued a decade's worth of her father's unfinished work after his passing, providing substantial contributions to a catalog of over 100,000 stars. Annie Jump Cannon was responsible for the Harvard classification scheme, which should really be called the Cannon classification scheme because she did most of the work on it. This is the basis for how we identify stars today. She could classify the spectra of up to 300 stars an hour, completing 350,000 stars in her lifetime. Henrietta Leavitt measured the distance between galaxies and discovered that Cepheid variable stars could be used as a standard candle for determining cosmic distances based on the brightness and what we see, leading to the modern understanding of the true size of the universe. These women were true astronomers, not just computers, and yet at the time their names were not always included in the papers published by their male counterparts. The book and movie Hidden Figures features some of the human computers at the National Advisory Committee for Aeronautics, or NACA, the precursor to NASA. These women were crucial to America's burgeoning space program. Katherine Johnson calculated the trajectory for Alan Shepard's historic flight, which sent the first American into space. Dorothy Vaughan specialized in trajectories for the Scout project, one of the earliest small satellite launchers. Mary Jackson started as a computer and worked her way up to becoming NASA's first female engineer of color. Her work in the supersonic pressure tunnel studied airflow, including thrust and drag forces that dramatically helped improve aircraft and rocket performance and efficiency. She authored 12 technical papers for NACA and NASA. By the late 1940s into the 1950s, the first general-purpose electronic digital computers entered the market, starting with the UNIVAC-1. The UNIVAC-1 gained attention by correctly predicting the outcome of the 1952 presidential election on live TV, where the human analysts got it totally wrong. However, as might be expected of the first ever digital computer, it was difficult to program and operate. So while NACA did have one, it wasn't used much. The human computers were still far quicker, more accurate, and reliable. Over time, though, the UNIVAC did prove that there was commercial viability to electronic computers. It didn't take long for a little outfit called IBM to get involved, releasing their first digital computer in 1951, with several other manufacturers not far behind. These mainframe computers were enormous, taking up full rooms and lots of electrical power, relying on vacuum tubes for most of the logic. These early computers were cumbersome and finicky. Instructions had to be precisely loaded one at a time, and one bad entry could crash the whole program or lead to unpredictable results, which sometimes meant the operators had to start from scratch. They were prone to bugs, in some cases literally. In 1947, an early computer was malfunctioning, and a team that included Grace Hopper discovered a moth causing a short circuit inside. The terms bug and debugging have stuck around since. Slowly, the electronic computers started to take over the work of the human computers. Even so, many crucial calculations were checked and validated by the human computers. Famously, John Glenn requested the calculations for the Friendship 7, the first manned American orbital flight, be rechecked by Katherine Johnson specifically before he would board the flight. Katherine also helped calculate the Apollo 11 trajectory for our first landing on the moon, and her work on backup procedures helped safely return the crew of Apollo 13 after the in-space emergency. And as I was writing this, I learned of the passing of Jim Lovell, the commander of Apollo 13, on August 7th of this year at age 97. He was also the command module pilot of Apollo 8, the first ever launch of a Saturn V rocket with humans on board. And they were the first humans to orbit the moon. So rest in peace, Jim, and thank you. Confidence in the electronic computers started to grow, in large part due to the human computers, who not only validated the computational results, they also transitioned into programmers and operators, like Dorothy Vaughan, who learned Fortran all on her own and taught her team how to program and operate the machines. The machines took over for the humans, so the humans took over the machines. In their new role as computer operators and programmers, the software on the machines rapidly evolved, and they were able to perform much more complex tasks, like simulating supernova core collapse to better understand these massive events. Through the 60s and 70s, computer technology evolved at a rapid rate, switching from vacuum tubes to these newfangled things called transistors, and combining several commonly used components into singular chips known as integrated circuits, or ICs, allowed computers to get substantially smaller and faster. Now, instead of taking up most of a whole room, a computer could fit within one bookcase-sized rack at a fraction of the cost. This made them more accessible for a wider range of applications. A Digital Electronics Corporation PDP-8 computer was used as part of the first ever fully computerized autonomous observatory, the Wisconsin Automated Photoelectric Telescope. This telescope could be scripted to perform a whole night's worth of observations on its own. It wasn't the most robust or reliable system, it broke down frequently, but it did pave the way for future telescope automation. NASA also built and launched the first ever space-based observatories by way of the Experimental Orbital Astronomical Observatory Program. The OAO missions proved the viability and value of operating observatories in space, and this led directly to the development of the Hubble Space Telescope. The satellites themselves had special purpose computers to read out the instruments and data from the devices on board and transmitted the data down to Earth via radio. On Earth, another PDP-8 computer was used to process that data and produce the scientific results. This was one of the first times an observatory was built and operated without a human to directly set up, operate, or observe the instruments, relying solely on the computers. These things were up in space. It wasn't like walking up the hill to the observatory if something went wrong. These missions also unlocked the ability to see beyond our atmosphere, studying both ultraviolet and X-ray emissions that would otherwise be blocked by the air mass that keeps us alive here on the ground. The 1970s saw even more progress in computing technology, getting even smaller, cheaper, and faster than ever. The microprocessor was a huge advancement, consolidating the functions of multiple integrated circuits and many transistors into one small package. Computers started to take over more and more telescopes, providing more precise control over the motors, ushering in go-to functionality and digital planetarium software. Increases in memory and processing power meant more and more complex calculations could be done. Graphics started to become a thing, meaning data could be visualized more effectively in graphs, charts, and even pictures. More importantly, computers started to become affordable enough to become household items, with the Altair 8800 becoming the first commercially successful personal computer. This was followed shortly by the Apple I in 1976 and the Apple II in 1977, which I'm sure many of you have at least heard of, along with the IBM PC, which became the basis for desktop computers as we know them now, and also coined the term of usage, PC. The late 1970s saw the world of computers starting to connect for the first time. Bulletin board systems, or BBSs, started popping up, where users could connect their computers over a phone line to other computers and share software, news, or just post messages as an early form of chat. Astronomers could share details of observations, compare notes, and coordinate observing campaigns, often collaborating with professional astronomers. In the early 70s, the government organization DARPA, the Defense Advanced Research Projects Agency, initiated a project called ARPANET, the idea being to establish connectivity between universities and research institutions to share resources and data in near real time. This allowed for an unprecedented level of collaboration and data access. Raw data from experiments could be remotely sent to researchers, and results published and shared significantly faster than waiting for physical media like paper, punch cards, magnetic tapes, or disks to be shipped across the country. The underlying technologies became the global network we now know as the Internet. Goes without saying, the Internet on its own was a monumental shift in communication and information sharing. Along with the breakneck pace of hardware advancements, software also advanced in leaps and bounds. For amateurs, digital planetariums continued to improve into the 90s and 2000s. Graphical capabilities became exponentially better. Nowadays, we have free software like Stellarium, a fully immersive and interactive 3D model of the sky. Smartphones brought the power of the computer revolution into our pockets. Apps of all kinds let you simply point your phone at the sky and it'll tell you what you're looking at. The evolution of programming languages has had a huge impact on the availability of software and how we interact with computers. The first electronic computers were programmed in assembly or machine language. To the untrained eye, assembly code just looks like minimalistic collections of seemingly random letters and numbers. It doesn't make any sense. But it does tell the computer precisely and explicitly what to do. Fortran was a little bit easier, but still no walk in the park. C, C++, and especially C are still very much in use today as one of the lower level programming languages that are practical to run on hardware, but they're still a little bit easier to read. JavaScript is built on top of C and used primarily on the internet to generate dynamic web pages these days. Python is likely the most prolific language in use today. It's one of the most human-readable languages, doesn't need to be compiled to run, and it can do almost anything. It's especially good at data analysis, thanks to some incredibly powerful support libraries or pre-written pieces of code, with almost every math or physics function you can think of. Most professional astronomers today will have to deal with some amount of Python in their career at some point. Within recent years, we've seen the rise of machine learning and AI, artificial intelligence. Machine learning is where a computer is trained for a specific task. For example, how to identify galaxies in a photograph. The training consists of a human loading photos into the computer and manually picking out the galaxies in each image. After a few hundred images are loaded, with galaxies pre-identified, the machine can generate a model using the human-fed data to figure out what common characteristics are and what a galaxy looks like in a photograph. It can then start to pick out the galaxies on its own in subsequent images with reasonable confidence. The training can be reinforced by humans confirming their correctly identified galaxies by the model, which further improves it. With enough data in the model, the machine could identify galaxies correctly upwards to 99.99% of the time. AI takes that idea to an extreme. By feeding the model with a much larger data set, basically the contents of the entire internet. Functionally, there isn't intelligence in the sense of the computer being alive or self-aware. An AI model isn't daydreaming or thinking about new things all by itself, but it is able to make what are sometimes unique associations between elements in the model simply because there's so much data to draw from. That means it can usually come up with some pretty good answers to pretty hard questions. There's also different models tailored for specific tasks. One might be better at being conversational and a chat partner to help bounce ideas off of. Another is good at helping programmers write fast and efficient code. And another can help you find the right equations to process a specific kind of data for a research project. Much like how humans can't fully comprehend how big space is or how big the universe is, it's hard to imagine how much information the AI models actually have access to. It's able to summarize the entirety of human knowledge and provide access to it through some simple conversational prompts. So we've just cruised through a bunch of computer history, but what does it actually mean for astronomy? From the time humans first looked up at the stars, there have been a few monumental shifts that unlocked further understanding of the universe. The first came with the invention of the telescope, letting the human eye see beyond its own physical limitations, showing us craters on the moon, details on the planets, and that the planets themselves have moons. The second came with photography. The ability to collect more light over time revealed structures and distant stars the eye could never see, even with the help of a telescope. It showed us there was more up there than we could have imagined. Spectroscopy started to give us an idea of what the stuff in the sky was made of, showing us the elemental fingerprints of stars, comets, planets, details our eyes physically can't see. Radio telescopes and the first space telescopes expanded our understanding of the universe beyond just light, as we started to explore ultraviolet, infrared, and X-ray emissions, and now neutrinos. So where do computers fit? With photography and spectroscopy generating so much data, computers were critical to extracting useful understanding from all that data. A photographic plate with some spectral lines doesn't mean much by itself, but when carefully calibrated, measured, analyzed, and compared to other plates, we can understand what the stars are made of. This in turn helps us figure out how many stars in the galaxy are similar to our own sun, and maybe find planets orbiting those sun-like stars that might be something like Earth. Computers enable us to do that so much faster. They helped us get up and out of the atmosphere, where we keep discovering new and exciting things from space. We can also detect and measure things that none of the 5 human senses can pick up on, from almost anywhere on the electromagnetic spectrum and beyond. Computers took us from the world of visual observation Galileo helped usher in with the invention of the telescope, with drawings, sketches, and handwritten notes, to getting up close and personal with the moon, with spacecraft like the Lunar Reconnaissance Orbiter. Heck, both human and electronic computers actually brought humans to the moon and back safely. And in case you're wondering, no, this impact crater is not the big one Galileo sketched. The resolution from the LRO spacecraft is so high, the whole image on the right would only be about the size of 1% of one single pixel placed on the image on the left. At this scale on the projection screen, the crater on the right would be about 1/10 of a millimeter. Computers brought us from sketches and grainy film images to being able to collect hundreds of photos per second. The computer can then sort them by sharpness, throw out the ones where the atmosphere blurred things too much, and combine the rest to produce a very clear image. I took the photo of Jupiter on the right last year with a 14-inch telescope. Over 25,000 images were taken in about 3 minutes. Only about 2,000 were good enough to get combined, but there's no possible way to do that without a computer. There were countless examples of computers processing large amounts of data into something useful or understandable. So here's a pretty neat example, and something that we at the McCarthy Observatory have started contributing to, thanks to Kevin Green and the Westport Astronomical Society. Occultations. Sounds kind of spooky, right? An occultation happens when something in space passes in front of something else. In this case, we're looking at when asteroids pass directly in front of background stars. When that happens, the light from the background star dims, like someone walking in front of the headlights of a car. We can measure that dimming, when it starts, when the star is at its darkest, and when it ends. With precise timing and location data, other observations along the occultation path can be combined, and something interesting happens. We can essentially compute the silhouette, or the shadow of the object, which can give us very precise details of the size, shape, and trajectory and speed of the object. The image on the right illustrates this nicely. Each colored line represents one observatory or telescope observing the asteroid 90 Antiope from different locations along the occultation path. We can see the observations dim for different lengths of time. The center part of the asteroid dims for a longer period of time than near the edges. The end result is a very good physical model of the asteroid, something that if we were to look at it directly with a telescope would just look like a tiny dot of light in even the biggest of telescopes. This ends up being a huge amount of data, typically captured as high frame rate video to precisely capture the moments of dimming and brightening from dozens of cameras and telescopes, synchronized to GPS location and time. It's impossible for a human to calculate all this, but relatively easy for a well-programmed computer. And that's not even considering the calculations of where the occultation path will be visible from Earth. Sometimes the paths are just a few hundred meters wide. Special software helps compute these paths and organize the observing campaigns to coordinate data collection. I think it's safe to say computers have redefined astronomy from simply viewing the wonders of the universe to starting to understand them at a far deeper level. With the ability to go beyond our own senses, make sense of the mountains of data and information they collect, and distill them down to something that we can wrap our heads around. Computers have helped to answer many of the questions our ancestors had about those bright flickering lights in the sky. And along with those answers came a whole new generation of questions for us and the next generation of astronomers to explore. This is an image from the recently commissioned Vera Rubin telescope. It's a very wide, deep field showing countless galaxies. This is just unbelievable. But computers help make that possible. So join us next month, September 13th, for our next Second Saturday Stars. If anyone's curious about vintage planetarium software, I did bring 2 vintage Apple computers to represent the 1980s and 1990s of where the software was at that time. So we can explore the sky with those if you'd like. They're set up in the warm room. And check out the Retro Tech Foundation's website at retrotechfoundation.org to learn more about our mission and goals. We currently have over 450 computers, and we hope to have the museum ready by late September for opening. Updates will be posted to the website as we get closer to the opening. And thank you.